Welcome to the next episode. We're doing the Giga scale model. So this is a scale factor of 1 to a billion. It's 1,000 times larger in scale factor compared to the previous one, which was 1 to a million. And we can now make a scale model of the solar system, but it's not going to be easy. You know, in all the textbooks, they always, when they have drawings of the planets and the sun, they always say not to scale, and that's true because of the size difference between the sun, the planets, and then the distance between the planets, which is huge. So I've come to this beach where I have 4.5 kilometers to play with, and we're going to make a scale model of the sun all the way out to Neptune. Well, the sun is 1.4 million kilometers across, right? And if we divide that by a billion, we have something that is 1.4 meters wide. Let me show you what I did here. This is going to be the center of our solar system. This is the sun, 1.4 meters across, and it contains 99.9% of the mass of the solar system. When the solar system was forming, almost all of it fell right into the middle, and that then created our sun. And the tiny bit left over, this is going to fly away, the tiny bit left over was in a disk of dust and gas, and that's what formed our planets. All right, so our first stop here in the scale model of the solar system is Mercury. I got the sun back, and we're at 57 meters away, which is the average distance of Mercury to the sun. So in real scale, that's 57 million kilometers, and the scale model is 57 meters. And the planet Mercury to scale is about 5 millimeters. I had a little steel ball that I dropped in the beach, but can't find it now. So here's the little rock. It's about 5 millimeters wide. And that is Mercury. And the sun is way, way back over there. And Earth is still more than, it's about 3 times the distance away. We're a little under twice the distance now from the sun compared to Mercury. This is the average distance of Venus. And it's 107 meters away. And the size of Venus is only this big, 12 millimeter size steel ball. Very similar to the Earth, very similar size. The Earth is just another 50 meters that way. We're now at the third rock from the sun, the Earth. And we're about 150 meters away. The sun in that direction looks as big as if I'm looking at the real sun. Relatively speaking, takes up the same angle. In the camera here, it's a bit of a wide angle, so the sun does look a bit further away, but it's all to scale. And here I have a marble about 13 millimeters large or across. It's about the size of the Earth relative to the sun. If we were any closer, like Venus or Mercury, we'd really be in trouble because there's just so much heat coming from the sun. And if we're much further away, we'd end up freezing. So luckily, here we are in the Goldilocks zone. Not too hot, not too cold. So what about the moon? What does the moon leave us here in our scale model? Let's include it as well. All right, so we got the sun, which is in the background over there, and 150 meters away. Here we have the Earth to scale. And the moon is about 380,000 kilometers away from the Earth on average. the orbit is a little bit eccentric, but on average it's about that much. And if we divide that number by 1 billion, we get 38 centimeters. And if we go out, here we have the moon. And the moon, when we look at it, the comparison of this little steel ball to the Earth is the same as, in angular size, as the sun in the distance is to the Earth. And that's why when you have a solar eclipse, the size of the moon and the sun are very close. So here we are at the distance of Mars from the sun. We're at 230 meters away. There's the sun in the background. It's certainly getting a bit chilly now. And we're out of the Goldilocks zone. We're into more approaching the icy zone of the solar system. Here is Mars. Tiny little ball bearing. And these are the 5 large objects of the inner solar system. Here, the biggest one is Earth, of course. If you add it all together, it's about 2 Earth masses. And 2 Earth masses is only about 0.5% of the total mass of the planets. So most of the mass of the planets, lies in the 4 outer planets, Jupiter, Saturn, Uranus, and Neptune. The gas giants, they contain most of the mass. And certainly they're much larger than these little guys in between. But we're lucky to live on one of them. All right, let's take a hike out to Jupiter. We're 780 meters away now from the sun, which is down over there. I've taken the balloon away just because it's a bit distracting for people, and I'm quite far away from it now. And we've gone beyond Mars, beyond the asteroid belt, and we're out now into the icy section of the solar system. And we come across our first gas giant, Jupiter. This is to scale, 1 to 1 billion. And just to compare, right, here we have the Earth, tiny little thing. And Jupiter's massive. It has over 300 times the mass of Earth. It contains more mass than all the other planets combined. So it basically operates as a shepherd dog for comets, and anything else coming through the solar system eventually interacts with Jupiter, most likely. The ancients really took note of Jupiter. It's quite bright. It was the main wandering planet, and they called it Zeus. The Greeks called it that, the king of the gods, and the Romans called it Jupiter. When Galileo first looked at it, something really fascinating happened. He noticed that around Jupiter there were 4 little dots circling it, and these were the moons. These were the Galilean moons, first discovered in the 1600s. And what was shocking about that, it was the first time people had noticed there's something other than the Earth for which you have something rotating around it. Right? Back then, in the Middle Ages, most of the world still thought in a geocentric sense. The Earth was fairly solid. They knew it was round, but they didn't really know it was spinning, and that we're the ones going around the sun. There were some Greeks who thought about this. Aristarchus of Samos, for example, maybe some of his work has been lost. But there were some folks who considered it. It was really until Copernicus who first had a more in-depth review of all the data, and he basically confirmed, right? Changed the world into a heliocentric world. Galileo at the time was a proponent of it, and through the telescope that certainly helped tip the scale towards a heliocentric viewpoint. Certainly the moons orbiting something other than the Earth was groundbreaking. A lot of people didn't want to accept it. And the other thing that really tipped the scales was the phases of Venus. right? So Venus, like the moon, has phases. You can see them from the Earth. And if you track the phases, you realize, there's no way that Venus can be orbiting the Earth. Basically, we're looking at Venus orbiting the sun. And that was another kind of geometric understanding of how things worked in space. Newton then, of course, came up with tying all of that with mathematics and the law of gravitation and orbits and that kind of thing. And that's how the universe really changed just a few hundred years ago. All right, let me show you the Galilean moons to scale. So we have Jupiter and its moons all laid out to scale. We start with Jupiter, and then we go to Io, which is the closest moon, and we go out to Europa, which is the icy moon, which a lot of missions are going to. Then we keep going way out here, and we have Ganymede. This is the largest moon of the solar system. And if we go way out over here, we have another fairly large moon, Callisto. All right, so we're on to planet number 6, which is Saturn. We've doubled our distance from the sun, which is still way over there. But at this scale, it's 1.4 kilometers away, which is quite a distance now. So things are getting colder, things are getting dimmer. Saturn was the last planet that the ancient astronomers knew about. It was quite a bit dimmer than Jupiter, even though the diameter is kind of similar, right? If you look at Saturn to scale, it's almost the size of Jupiter. It is a lot less dense, though. It's only about 100 Earth masses, a little less than that, compared to Jupiter. But was the last known wandering planet, and it moved the slowest, right? Because Saturn has the biggest orbit compared to Jupiter and the other planets we've seen so far. And this is before Uranus and Neptune were discovered. We've doubled our distance once again. Saturn was at 10 astronomical units, and the next planet, planet number 7, which is Uranus, is at 20 astronomical units. So the spacing of the planets is getting more and more further away from each other. Probably it's a reflection of the amount of mass in the disk as the solar system was forming. And Uranus and the next planet out, Neptune, they're also quite a bit smaller than the gas giants. This is the scale model, 1 to a billion. It's still rather massive compared to the Earth, but it's kind of medium-sized compared to Jupiter and Saturn. They're sometimes called the icy giants because they live in the icy parts of the solar system that are far out. So we're now 2.9 kilometers away from the sun, which is way over there. And from this distance, if we were on Uranus, the sun probably would just be like a point of light. It'd still be bright in the sense you could still you'd read by the light. It'd be much brighter than the full moon. But looking at it, you just wouldn't be able to see a disk because we're so far away. And Uranus also has rings. I don't have them shown here. They're very faint rings. And its twin planet Neptune, which is further out, it has some rings too. And of course, lots of moons, right? So these 4 large planets in the solar system, they have more moons than we can count. We keep discovering more year by year, which is great. Welcome to the last stop on this beach. This is where we have the planet Neptune, planet number 8. It's the furthest out from the sun. The sun now is way, way over there. It's about 4.5 kilometers away. Neptune is just like Uranus. It's the same size. And it's another icy giant. Like Uranus, it has moons and it's got some faint rings. Everything beyond Neptune doesn't really fit on the scale model. I don't have any more beach to go to. And even if I did, things like dwarf planets, which is one example of Pluto, and other smaller objects would appear like grains of sand. They would be so small to see at this scale of 1 billion to 1. Beyond that, we get to the Kuiper belt, which are objects that never formed into planets. They're just at an extreme range from the sun, very hard to see. And beyond that, we get to the Oort cloud, which are just a bunch of primordial comets that envelop the sun. To go any further, we need to really jump to the next scale, scale factor, which is 1 to 1 trillion, which is the Terra scale model. And that's where I will see you next.